Thank you, Thibaut, for inviting me. The work I'm going to present to you was of interest to our growers in the North Coast. So when Thibaut asked me to talk about managing phenolics in the vineyard, I thought we could go through some basics like he did previously, and then we'll move on to the applied study. I'd like to acknowledge the actual people that did the work. Johan Martinez, who's also in Oakville. Chris Chen is a master's student. Luca Brillante is going to talk to you as well in a little bit in the afternoon. So the main goal is to get the phenolics in the wine. So you have some organoleptic properties that affect the sensation. Firstly, it's a visual sensation. You know, you have the color, and then you have copigmentation with the interaction of anthocyanins and flavonols. And then we have a tactile sensation, like Thibaut talked about, which comes from the berry skin, which is driving astringency. And of course, you have a taste sensation, which is a bitterness, which is coming from the seeds. Of course, there are health-promoting effects, and it's an important antioxidant capacity as you consume more wine. So I have this figure here that looks at the intensity of color hue of different cultivars, starting with Merlot, Cabernet, Malbec, Syrah, also Shiraz, Mourvedre, and Petit Syrah. Some of these cultivars we don't necessarily grow, but looking at the marketplace, this is the usual color intensity, which is the contribution of anthocyanins to the wine. Of course, the flavonols also impart a feel in the mouth feel of the wine. This is wines that were made with either addition of skin flavonols, which is quercetin 3-glucoside, both for white wine or red wine. White wine, the control is the dotted line. The red wine is the red dotted line. The adulterated wine are the solid lines. So we tend to get an intensity of astringency in the red wine and roughness with the addition of flavonols into the wine. Only the glucosides are present in the skin. You see the quercetin in the wine in the end. We talk about proanthocyanidins, for lack of a better word, tannins. These are important due to their astringent properties, and they have a role in long-term stability, like Thibaut mentioned a little while ago. We have grape-based proanthocyanidins. Other species have proanthocyanidins as well. But in the grapes, we're mainly looking at catechin, epicatechin, epicatechin gallate, and epigallocatechin. Skins versus seeds. Skins contain epigallocatechin. They have a greater degree of polymerization, and these skin proanthocyanidins are the ones that form the reversible bonds with the salivary proteins to give you that puckering sensation. The skin proanthocyanidins will also have a lower proportion of gallulated subunits, which might affect bitterness. So you can use this information to relate to tactile and taste sensation. Increases in tannin molecular size will increase astringency. You can increase the molecular size of the proanthocyanidins by cultural practices, and then increase astringency in the field. You can increase the percentage of epicatechin gallate with cultural practices to increase drying and chalkiness. You can increase the proportion of epigallocatechin in the skin to lower the coarseness, to make the fruit more velvety, and hopefully this can be extracted into the wine. And as you increase color incorporation with the skin proanthocyanidins, you will have a less astringent wine or fruit with less of a bite that can be more smooth or velvety. So all these things are of important to us, but they're coming from the plant itself. So products from the phenylpropionate pathway are of interest in viticulture and therefore in wine. We have various compounds that are of interest to us. We have the flavones. That's coming immediately off the pathway. We have the flavonols that are going to be upregulated by increased light transmittance into the canopy. And then after this, you can branch into your catechins, and then your tannins, finally condensed tannins. Or you can upregulate this portion of the pathway. In the end, you're going to end up with anthocyanins. Well, so let's look at a little bit of the pathway in detail. So everything's coming from the ischemic pathway. You're going to have this two parallel downstream pathways. Your products can be either dihydroxylated or trihydroxylated. We can manipulate the hydroxylation pattern for anthocyanins or flavonols either by light exposure or when you introduce a deficit to the berry. We prefer to have more trihydroxylated compounds, whether in the berry or in the wine, because you have more of a chance to make these compounds more stable. These trihydroxylated ones would be your petunidins, malvidins, branching out from delphinidins. Your pinkish compounds are going to be more dihydroxylated or 3,4 substituted, and they usually peter out in the end. So looking at the 3,4 substituted, they will follow this pathway. Again, O-methyl transferase catalyzes this pathway here. Your 3,4 substituted ones, again, will require O-methyl transferase to go from delphinidin to petunidin and then malvidin. So these are your 5 base compounds that make up the anthocyanin profile. So these 5 base compounds can either be acylated or methylated in the end. So overall, we're monitoring for about 15 compounds in the grape berry or in the wine to make up the grape profile. So in the anthocyanins, we have this other weird compound. This is uncommon in Vitis vinifera, so I'm not going to look at that. Your disubstituted or 3,4 substituted anthocyanins are going to be cyanidins. Your trihydroxylated or 3,4,5 substituted anthocyanins are the delphinidins, and they will branch out from here. The flavonol homologues for disubstituted flavonols is going to be your quercetins. Pelargonidins are going to be your camphorols. Your trihydroxylated flavonols are going to be your myricetins in the end. Of course, we have a variety of differences and effects of management practices. Thibaut just a moment ago showed the effect of leaf removal. So this is Cabernet Sauvignon and Sangiovese. The colors indicate the intensity of hue of the 5 base compounds that we normally monitor, such as delphinidin, malvidin, petunidin, cyanidin, and peonidin. Cyanidin is essentially pink. You see it mostly in Zinfandel, sometimes in table grapes. Peonidin is this brickish red color. Petunidin is somewhat of a baby blue. Malvidin is turning purplish. Delphinidin is really dark. So a Cabernet Sauvignon shoot with 12 leaves has quite a bit of a variation in the profile, but you can manipulate this by just retaining 3 leaves around the basal cluster to change the profile of this quite readily to more malvidin based and remove the influence of peonidin. Sangiovese is more difficult to elaborate these results. Again, retaining 12 leaves or 3 leaves manipulates the cyanidin composition. However, as you do more leaf removal in a cultivar like Sangiovese, you increase the proportion of pink. So that might not be as desirable. Of course, we have an effect of water deficits on profiles. Usually, as we do cultural practices, either pre-veraison or post-veraison water deficits will affect the color concentration and content in the berry. However, the trihydroxylated substitute compounds will predominate with water deficit, as the F3,5H expression levels will increase after veraison. So depending on what market you're going after, or what the winemaking style is, we have years of data to back this up, how you can manipulate this pathway, whether you're going for more of a pinkish hue or more of a darkish hue, by imposing a water deficit in this case. So like I said, this trihydroxylated forms will predominate with water deficit, as this expression of the trihydroxylated ones will increase post-veraison. The effect of water deficit on wine hue is somewhat known. We have various data both from California and Washington State. So we have a late deficit industry standard, late deficit industry standard 2. So looking at these, most of your color saturation, dryness, surface texture, and purple hue is going to be optimized with an early deficit. And early deficit would be described as between fruit set and veraison, when you cut down the water application by about 50% of crop evapotranspiration. Usually, industry standard is known amount of deficit throughout the whole season without introducing any regulation in deficit. We usually end up with a brown hue or a red hue, which would indicate to me that the dihydroxylated forms of anthocyanins are predominating in this case. So it might be wise to work with a crop advisor to look at the timing of early deficit after fruit set, without slowing down shoot growth in the early season to maximize this color saturation. So we have the summer ultraviolet daily doses changing. So whenever I give these talks in other regions, people mock me. This is not happening. This is climate is not changing. It is actually changing. Area thermal ultraviolet radiation that we're receiving is changing. So we see this heavy load in Chile on the coast, and then we see it increasing on our coastal areas as well. So we're under these heat spikes. We had a prolonged drought. Not only that, we have this high ultraviolet light gain falling onto our vineyards. So not only vineyards are being affected, stone fruits like peaches, nectarines, apples, pip fruit is also being affected. So we have less cloud coverage and increasing temperatures, which ends up resulting in a yield loss. This yield loss can be direct due to berry water content decreasing, resulting in shriveling. But more importantly, it's indirect. You have a changing in acidity, astringency, and color hue. We don't necessarily, worry about, pushing these giant yields in the north coast above 12 tons to the acre. So our yield loss in this case is indirect, because we have shifts in phenology, and then we have compositional shifts in the flavonoid profile of the berries that are coming out of the farm gate. So with that in mind, we have this experiment at Oakville Station. This was a 4-year-old producing vineyard, Cabernet Clone 7 on C3309. Spacing is 6 by 8, almost running north-south. This is a bilateral cordon on a relaxed vertical shoot position. So in this case, we looked at 5 colored shade nets. So as you drive up and down 29, you see a lot of them. There's a lot of interest in them. And then we compared this to the untreated control, and then we imposed 2 applied water amounts in a split factorial to test the effects of this shading. These 5 polyethylene cloths, they have about 80% transmissivity of visible light. That's what the company advertises. So we looked at blue, pearl, aluminate, which has this silver coating, red, and black. And we did this on and also comparing these to an untreated control. So we essentially covered the fruiting zone about like in 3 feet of area. And this is how we applied them. Let's see what they do. The irrigation treatments we used a sustained deficit. 65% of estimated crop evapotranspiration was applied from fruit set to harvest. Or we did a regulated deficit. SDI was applied soon after bud break, but we decreased this to 25% of ET crop from fruit set to veraison. And then we ramped it back up so we don't lose the yield at this site. So results. My table is not showing up. Apple. I'll just tell you what the nets do. The nets work as they recommend them. So they filter out about 20% of the visible light. However, they also affect the ultraviolet light A, ultraviolet light B, ultraviolet light C, red, green, and blue wavelengths. So I had these in percentages how much they filter out. So yellow is an open field. Green is control, blue is the blue shade net, pearl is that white one, black is black, red is the red one, this is the aluminate. This is the wavelength in nanometers, and this is the intensity of these wavelengths that are transmitted through to the cluster. So you can see that we have a wide range of wavelengths that are being manipulated by these shade cloths that we're putting on the grapevine. So this was measured right at the berry, or at the cluster level. So what does this do? Anytime you shade something, you're going to change the temperature, right? So here's the morning side. We start out at 6 in the morning. We go till about 8 o'clock at night. So I'm thankful for people who can measure these, staying overnight at the station. So we're going from we're starting at like 10 degrees Celsius to about 40 degrees Celsius. This is the morning side of the canopy. Afternoon side of the canopy, starts out at like 10 degrees Celsius, but goes all the way up to about 48 to 49 degrees Celsius in the control. That's about 120 degrees Fahrenheit. These are berry temperatures. So you guys have been, in this business for quite a while. 48 degrees Celsius on the berry is probably not good. So to summarize this, looking at the evening side that's on the exposed, so this is the ambient curve, okay? This is the shaded curve, and this is the uncovered curve. So uncovered curve is reaching a peak at about 120 degrees Fahrenheit. This is during the sugar loading and anthocyanin accumulation phase. And this temperature regime lasts a good 6 hours every day, starting at 12 degrees Brix. So that's probably not good. So, so looking at the components of yield, so these are the interactive effects. We had an interactive effect of these colored shade net covers and applied water amounts on the yield per vine. We had an effect on our berry mass based on the nets. So the berry size was increasing by black shade nets because that did not create any scattering of the light. It was just transmitting straight through. However, this did not necessarily translate into a statistically different yield. So when we combine aluminate with a sustained deficit irrigation, we were seeing this about 24%, 25% decline in yield, because this aluminate, as the light was passing through it, if you could have seen that table, it's also reflecting the light out, but it's also reflecting the light back into the canopy. So we had a lot of tissue death in this shade net cover. Now the million-dollar question. What does it do to the anthocyanin profile and our pro-anthocyanin profile? So we were not expecting this. In vines without nets, in the control, the exposed berries did not make it to the end of the experiment. So since we did not make wine from it this year, AVF didn't fund this study, we could not capture the effect of this in the wine matrix. However, we have these differences in berry mass and also in total anthocyanins. But more importantly, the anthocyanin hydroxylation profile is changing based on the irrigation method that we apply. So if we introduce a regulated deficit irrigation to the blue, we're getting the most beneficial hydroxylation profile, meaning that we have more of a stable compound in this case. Looking at the mean degree of polymerization, for lack of a better word, astringency of the skin and the seeds will have less astringency, so this is more of a taste. This is more of a tactile sensation. The shade nets or applied water in 2016 did not affect it at harvest for skin mean degree of polymerization. However, we have an interaction of shade nets and applied water amounts on a seed mean degree of polymerization, meaning that blue irrigated with a regulated deficit irrigation is going to be less bitter. So looking at some of the other ones, when we apply control with RDI, we have a lot of bitterness. Again, with black, red, aluminate, we have a lot of bitterness. But again, we could not make the wine from these this year to see how this transfers into the wine matrix. So solar radiation exposure can equilibrate berry acidity and promote anthocyanin biosynthesis. However, extreme temperatures will lead to organic acids and anthocyanin degradation. So we have more data. So we took this development of flavonoid and acid profiles 5 times during the season with gene expression samples. So we'll have more of a detailed presentation as data accumulates. We saw a 3.5 degree reduction in temperature at the moment of our highest berry temperature, but this reduction was not necessarily associated with ameliorated berry composition and the primary metabolism. Uncovered grapevines often displayed a greater level of proportion of berries with sunburn, sunken tissue, or raisioning or mummifying. So primary metabolism, we have a yield reduction with aluminate, RDI irrigation treatment. We had a greater bricks or faster bricks accumulation, as well known. Secondary metabolism, hydroxylation of anthocyanins to trihydroxylation was greater with blue and regulated deficit irrigation. We had no measurable effect on skin mean degree of polymerization at harvest. So this is a tactile sensation. Seed mean degree of polymerization, control irrigated with a regulated deficit, we had a greater bitterness, so this would be a taste, so it might be undesirable for premium vineyards. Seed mean degree of polymerization was less with black or red covers with a sustained deficit irrigation, or blue with a regulated deficit irrigation would lead to less bitterness. So thank you for listening. Do I have time for questions, or did I blow over the time?
No, you can have a few questions, but we have no question on Slido.
How do you measure the mean degree of polymerization?
We measure the mean degree of polymerization with a reverse-phase liquid chromatography. So we extract the skin tissue in acetone, skin and seed tissue in acetone. We cut it with fluoroglucinol, and then we divide it into its subunits and terminal subunits. Then their molar contribution to from the terminal or the subunits will tell us how much polymerization is in the skin or the seed. So depending on the gallulation, it'll tell us whether it's coming from the seed or the skin. So skin tannins will have more polymerization, so astringency or the tactile sensation of this is high. So at larger wineries, it's becoming more routine to look at a mean degree of polymerization. And we have it set up at Oakville as well at our new lab. So we can look at it too. So rather than just looking at a concentration of tannins in a known matrix, so this divides it into its subunits and terminal subunits. So you can classify which ones would interact with the protein salivary glands or not, basically. There are other tests for chemical activity, how much it would stick to your tongue, for example, or your mouth cavity. But those are more involved, more on the wine side, which I don't quite understand as a viticulturist. So it seems to be metaphysical to me. So, but anyways, so enology faculty looks at that, not me.
Can you bring the mic to Steve?
You saw differences in hydroxylation with water and light exposure. Did you see differences in acylation patterns?
I haven't calculated it yet, but yes, of course, we see more acylation with early deficit. So the original talk that I was going to give looked at leaf removal in a very warm climate. So there we saw more acylation with those as well.
When you see these variations, do you know whether it's that there are forms that are more resistant to degradation, or is it that there's synthesis occurring?
That's an excellent question. I was hoping someone would ask it. So, so we're seeing an uncoupling of sugar accumulation in the berry and anthocyanin content starting at around like 17 degrees Brix. 2016 was a very interesting year. I work. I have a statewide appointment. My wife hates it, but I like it. So we go from all the way down to Bakersfield area, south of Bakersfield, all the way to Ukiah. So starting at 17 degrees Brix, we started seeing the anthocyanin content per berry peak. So let's say it was around like 3,000 parts per million at that point. By the time technological maturity occurred, in this study it was 25 degrees Brix. We were roughly 43% of that. So how they degrade is dependent on how this irrigation was applied. So we need to pay more attention to how we introduce this irrigation into these vineyards, whether it's in like 2-hour drinks, 8-hour drinks, at what stage it's going in, and what portions of the vineyard are getting this water, because soils are not uniform anywhere you go. Yeah. All right.
Okay, well, Kaan, thank you very much.
Thank you.